I'm Farrar, and I'm going to be going over Chapter 8, Induction Machines. So in Chapter 7, we learned about synchronous machines, which works by supplying a DC source to the rotor and an AC source to the stator. In an induction machine, an AC source is still supplied to the stator, but no source DC or AC is applied to the rotor. The AC source in the stator produces the same rotating magnetic field, and because this magnetic field is rotating, there's a change in magnetic flux through the rotor. This changing flux induces a current in the rotor, and this current produces its own magnetic field. This magnetic field produced by the rotor is attracted to the rotating magnetic field in the stator, and as the stator's magnetic field rotates, the rotor will rotate to follow. In motors, the stator magnetic field is faster than the rotor, and in generators, the rotor is faster. There are two types of induction machines, wound rotor induction machine and squirrel cage induction machine. The wound rotor induction machine seen on the right in figure 8.1. How it works is it connects the windings of the rotor to each other via resistive elements through brushes as seen in the figure. And then squirrel cage induction machines, they are shorted, the windings are shorted together with a shorting ring as depicted in the figure. So to go over the relative speeds and frequencies of the different things going on inside of an induction machine, this first equation here, F is equal to P S sub S over 120. This is the same equation that we talked about in chapter 7. F is just the frequency of the stator magnetic field, P is the number of poles, and N sub S is the synchronous speed in RPM. This next equation, omega sub R is the angular frequency of the induced rotor current. Omega sub S is the angular frequency of the stator magnetic field, and P is still the number of poles, and omega sub M is the angular frequency of the rotor. In synchronous machines, omega sub R is going to be equal to 0. This is not the case for induction machines because, as discussed in the last slide, the current induced in the rotor is due to the AC source in the stator. So as the magnetic field rotates, the current in the rotor is going to be changing. And that takes us to slip. So slip in induction machine. In synchronous machines, the rotor and stator are in lock. The rotation between the magnetic field and the rotor, they are in sync. They're going at the same speed, hence the name synchronous machine. In an induction machine, this is not the case. When an induction machine is acting as a motor, the rotor is going to be spinning slower than the rotating magnetic field. And then in generators, the rotor is going to be spinning faster than the synchronous speed. So in motors, when the rotor is spinning slower, that is going to be a positive slip, which is represented by the variable S. And in generators, when the rotor is faster, the slip is going to be negative. And the equation for slip is going to be the speed, the synchronous speed, minus the speed of the rotor divided by the synchronous speed. So if we imagine this right here, this fan as an induction machine, to understand why the rotor cannot be spinning at the same speed as the magnetic field, we can think about how it works with a fan. So if the rotor were to be spinning at the same speed as the synchronous speed, then there would be no change in flux inducing a current in the rotor. So there is no force being experienced by the rotor. But while the fan is spinning, air is going to be opposing its rotation, slowing it down by providing an anti-torque. And then eventually the rotor will be spinning at some speed where the torque produced by the air and the torque produced by the rotating magnetic field being faster than the rotor, well, these two forces will equalize, and then the rotor will operate at a constant speed. And then in generators, we have the wind turbine as an example. The wind propels the turbines to spin. And then this spinning, if it's faster than the rotating magnetic field induced by the AC source being supplied to it, current will actually be delivered out from the induction machine, making it a generator. So right here is a schematic of an equivalent circuit for an induction machine. RS is going to be the stator resistance. X sub LS is going to be the stator flux leakage. X sub M is the magnetizing reactance. X sub LR is the inductance of rotor referred to stator. And R sub R divided by S, where S is the slip. It represents the transfer of electrical energy to mechanical or vice versa, depending if it's a motor or generator. The Thevenin equivalent components of the circuit can be found using these equations right here. V open circuit is going to be equal to VA times JXM divided by RS plus JXLS plus JX sub M. And then Thevenin equivalent impedance is going to be equal to J XLS XM divided by XLS plus XM. And this term that makes up the fraction is the same thing as X sub TH. If RS right here is 0 and XM is much greater than XLS, then the circuit can be simplified to just three series components, XLS, XLR, and R sub R over S, because JXM, because it's so large, essentially becomes an open circuit, and RS is short-circuited. So now we're going to look at how power is transferred through an induction machine. So this first equation here is the power that makes it across the air gap between the stator and the rotor. That's going to be the power through this branch or this part of the equivalent circuit right here to the right of this node. So to find this, because power is the real component of our power triangle, it's going to be 3 times the current in this branch times the real element in the impedance on this branch, R sub R over S. And well, the current's going to be squared, 3 times the current squared. And then I put this equation right here too, because one of these in the slides had this notation, and then the textbook had this notation. So I included both of them just to make it clear that they're the same thing. And then this next equation is the power that is lost due to the copper winding in the rotor. It's going to be equal to 3 times the same current squared times R sub R prime. So it's just going to be PAG times S. And then the mechanical power outputted by the rotor is going to be equal to the power across the air gap minus the losses in the rotor. So it's going to be PAG times 1 minus the slip. This is for the output of a motor, and to make it as efficient as possible, we want S to be as small as possible so that there's very little loss going on in the motor. And this equation right here is a simplification following that there's no other following the assumption that there is no other losses outside of the losses due to the winding in the rotor. for example, another loss could be flux leakage in the stator. And then efficiency is just going to be the output power over air gap. So just the power through the air gap, so 1 minus S. So the last thing I'm going to go over is torque, max torque, and speed torque characteristics. So the torque of an electric for an induction machine is given by this equation right here, and it's just in terms of all the components that make up the equivalent circuit that we've discussed the past couple of slides. The slip at which the induction machine produces the most torque possible is going to be given by this equation. So if we just want to know how much torque an induction machine can produce at its peak, we would just take this expression and plug it into S here. Speed torque characteristics. This is about the relationship that emerges between the speed and the torque at a given speed for an induction machine. So that's seen right here on the right in this figure. The x-axis is the speed in RPM, and the y-axis is the torque. So it starts at around 200, decreases, and then starts ramping up, peaks at around 1700 RPM, and then suddenly takes a sharp turn downwards. Different induction machines will have different looking graphs. Squirrel cage induction motors, they're going to have a lower starting torque, and wound rotors are going to have a much higher starting torque. So that's one downside of a squirrel cage. Additionally, if we go back to the wound rotor from the earlier slide here, these resistive elements right here, by changing these, we are able to get different speed torque characteristics from our induction motor.
Here's an example problem we can work through together for practice. The problem states that a 3-phase, 60 Hz, 866 volts, line-to-line, 6-pole induction motor is operating at rated voltage at a speed of 1,170 revolutions per minute. The per-phase equivalent circuit is shown below. Now, they ask us to solve for PAG, PM, and the torque in Newton meters. So, first, let's start off by listing what we know. We know that the frequency F is 60 Hertz. We know that the line-to-line voltage, or I guess we're going to make it per phase, right? So let's make it VA is equal to 866 volts for its magnitude. And while we're there, let's set it as reference and say that the phasor is as such. We also know that the induction motor is operating at a speed of 1,170 revolutions per minute. So that would be the actual speed of the rotor, which is this. So for now, this is what we can write. We also know that P is 6, since it's a 6-pole induction motor. Okay, so we have this circuit, and we're wondering, what should we do with this? So the first thing we'd want to do is solve for the Thevenin equivalent. So we do that by using Thevenin's theorem. Thevenin's theorem states that any linear circuit, regardless of its complexity, can be simplified to an equivalent Thevenin circuit, which consists of a single Thevenin voltage source and a Thevenin series resistance connected to a load. So we'll start with finding the Thevenin resistance, which in this case would be an impedance, right? So we'll write it here. We'll say ZTH is going to be these two, right? We're going to combine these two, and we're going to say that it's 27J times then. So that'll give us as the impedance. And for the Thevenin voltage, we'll do this. This will get us the voltage across, right? This will give us the Thevenin voltage source for the equivalent circuit. So this will be 27. Oh. And then we have to multiply this by the voltage source, because it's like a voltage divider. All right. Oh, and we do this because it's per phase, right? So that right there should be like that. My apologies. So that would be, yeah, that's because it's per phase. And so we should be getting, I believe, let me make sure, we should be getting like 450. And that would be with 0, right? Because that's also 0. So I drew the Thevenin equivalent circuit right here, using the values that we saw for just now. And so right now, it's not directly being used, like this circuit's not directly being used, but it will come in handy in a second. So what we want to solve for first is the synchronous speed, because eventually we're going to need all of this to combine. We're going to use all of these values to solve the power across the air gap, the mechanical power, and the torque, right? So it's like, it's kind of cascading. So the first thing I guess I'll do is I'll solve for the synchronous speed. So the synchronous speed can be found using this formula, where this is the synchronous speed. And this is the frequency. This is the how many poles each phase is wound. So, and then this is just a constant. So we can rearrange this and say that the synchronous speed is the frequency multiplied by 120 divided by the poles. So this will be 60, 120, and 6, which should give us 120. All right, so with this, we can start solving for some later stuff. It won't seem like it's useful right now, but it is. So we're going to solve for the frequency of the rotor. And that's going to be S times F. And omega times 2 pi. This is the angular. And so, right, what's S? We haven't solved for that. Well, we're about to solve for that. So S is the slip, which is that synchronous speed minus the actual over the synchronous. And this is important. It gets used all throughout the problem. So this is going to be equal to, what would this be, 1? And then I think it was, yes. It will be, I believe this will be 0.025, and I think it's unitless. So then we can use that to solve for this, which will be, so we'll get that the rotor current frequency is 1.5, and the frequency of induced currents in the rotor is, I believe, 9.42. So that's not useful right now because, right, like we haven't seen something that needs it, right? Right now what we want to solve for is the current, this one, IR, because that will help us solve for the powers, right? But eventually, this will be necessary, so I thought it'd be good to get it out of the way now since we're already working with the frequencies. So let's move on to solving for I. So the formula for this is VA for RA plus R. Where this is the stator resistance, this is the rotor resistance referred to the stator side. These two are the leakage reactances of the stator and the rotor referred to the stator side. And I would say that these are very similar to the transformer equivalent circuits that we did a while back. I think like the solving it and the way you set up the circuit's similar. So we have all these values. So we know that the rotor current is equal to, so what is VA? Well, it's VTH, which is 450, right? And then we divide this by, so the stator resistance is 0. We don't have one if you look at this circuit. And so that would be 0. And the rotor resistance with, like, referred to the stator side is simply this, what I just circled right there. And it's divided by S, so it's 0.025. And then this is multiplied by J and the leakage inductances, or not inductances, reactances, which are these two things. So where I put these. And so that'll give me a rotor current of so that's my rotor current. So here's where we start to solve for values that the problem asked for, right? So instead of solving for things that would help us solve for these values, right? So, right, this wasn't directly asked for. We're now solving for those things. So we're going to be able to solve for PAG, PM, the torque, right? So now we focus on that. Now we've set up, so now we can start solving. So we know that the input power is equal to 3 VAIA cosine phi, where cosine phi is the power factor between VA and IA. So we could use this, or we could use another relationship, or I guess another formula for total input power. So this formula says that the total input power, PT, is equal to the following. Now, what is this? Like, what are we looking at, right? Well, actually, this entire input power, right, this total input power is made up of 3 different little powers, right? So this is the power across the air gap, PAG. This is the stator copper loss. And this is the core loss. So we can actually use this to solve for PAG, which would be equal to 3 IR squared. Right, so we want to find the power across the air gap. It specifically asks us to do so. So we already solved for IR, right? So if we go back and we say, okay, 21.83. Okay, so actually in this case, let me make sure that we understand this is, or I guess I'll use an arbitrary, like A versus A. This is a phasor, this is a magnitude. In this case, this formula is asking for the magnitudes, so we're just going to put 21.83. So PAG is equal to 3, 21.83. Then I believe this was, our R was 0.5, and this was 0.025. And that should give us a power across the air gap of 28592.91. So now that we have the power across the air gap, we can actually directly solve for the mechanical power. The mechanical power is equal to this, right? So we could use this again, right? Like this is something we can use, but it's also equal to this, right? So that relationship, this little thing right here, is PAG. So why even go through all the effort of recalculating it when you just did? So we find then that PM is equal to 2787814 watts. Now all we have to solve for is the torque in Newton meters. So solving for torque from here is fairly straightforward. So here's the symbol for torque, and it's equal to the mechanical power divided by the mechanical speed in mechanical radians per second, right? So from here, we want to know what this mechanical speed is, right? So this is actually equal to this. It's also equal to 2 pi, I believe it's 2 pi NACT over 16. But in this case, I want to use this. And so what's WS? Well, or not W, omega S. Omega S is also equal to this, where we can shift this around and we can get that omega R over S is omega S, right? And so omega R we saw for earlier, and we got that it was 9.42 radians per second. 9.42 over 0.025 will get me omega S, right? And then I plug that in there, right? And I get that it's whatever omega S is. And we plug this, right? We get omega S 1 minus S PM. Now, if this was a 2-pole machine, we'd be done here. But because it isn't, we have to multiply by poles divided by 2, in which we already solved that the poles, well, it tells us that it's a 6-pole, right? So it's P over 6. It's P equals 6, so 6 over 2. So then we get that torque is equal to PM, which I guess, what was it? It was 27878. 27874, I think. Yeah. And then times 3. Then I think WS, I don't know what that is off the top of my head, but we get this to be Newton. So this is what you should get as your final answer. And that's it for part A. So moving on to part B, we want to find what the maximum torque is and the slip at which it occurs. So in order for this to have a max value, we need the derivative with respect to S be equal to 0. So after that, to find the slip at which the maximum torque occurs, it basically has to do with the maximum power transferred to the rotor resistance when this resistance is equal to the impedance, right? So we find that this is given, right? We should know this. But this is a special case where RA equals 0, right? We already said that. I think over here we said RA was equal to 0, right? And then we can change this, or not change it, but we can say that this is this. So this will be the maximum slip. Or I guess the slip at which the maximum torque occurs, right? And so if we plug in, right, we get, which should be 0.1, which is different from the original value, which means our omega changes. So that frequency, FR, is now different. So we have which is 6, and then which is 12 pi. And then we use that over here and we get that 12 pi over 0.1, which is omega s, which will be used. Since this is a multi-pole induction motor, right? It says it's 6-pole induction motor. Induction motor. To get max torque, it's a bit different than just the ones before, like the multi-pole. So the formulas are similar. The only thing that changes is the amount of poles being included divided by 2. Because and this is just an aside, for the expression for max torque otherwise, if it's not multi-pole, this is a side. Right. Is just this. But since it's multi-pole, it's 6-pole, we use this one. And so we just plug in, right? So we solved for this earlier. We solved for the new one. So it's 6 divided by 2, since it's 6 poles, 3 halves. Then 450 was the VA we solved for. Omega S was 120 pi. And then these are the same as before. And we should get that it's 483.4 Newton meters. Which is what was asked of us. We found the max torque, and then we found the slip at which the max torque occurs, which means we've solved this problem in its entirety.
Okay. Howdy, everybody. My name is Billy Faulk, and I will be solving a problem on induction motors. So, in this problem, we have a 3-phase, 6-pole, 440-volt line-to-line with 60 hertz and a Y-connected motor that has a leakage resistance for the stator that is equal to the leakage resistance of the rotor, which is equal to 12 ohms. We have an XM equal to 40 ohms. And we're going to be trying to first find an approximate equivalent circuit to find the rotor resistance, such that the slip at the max torque is going to be equal to 0.1. And then from there, we are going to be trying to find the torque at the electric origin, torque of electric origin, my apologies, as a function of the slip. And we're trying to also find the starting torque at from electric origin. Okay. So I think that the best thing though to do, or the thing we should do first, is we should try and find our approximate equivalent circuit, right? This right here. So we're given a line-to-line voltage, and what we can do is, in order to get that to a per phase voltage, we can divide that by a square root of 3. So our VLL is going to be or is equal to 440 volts, and we're going to get that to voltage per phase. So it's going to be 440 over square root of 3. Okay. All right, so that's going to be our voltage. So from there, it's going to be pretty straightforward to drawing the equivalent circuit. So let's draw the equivalent circuit. Equivalent circuit. Okay. So we're going to have an XM value here. But let's real quick put in our 440 over square root of 3 volts. And it has an angle of 0 degrees, but we won't add that in here. Okay, we'll also add in our XM value. So our XM value is 40J, right? And then now we need to add in our leakage resistance for the stator and our leakage resistance for the stator. I'm sorry, sorry. Our leakage resistance for the stator and our leakage resistance for the rotor. Okay, there we go, there we go. So here's our, let me fix that real quick. So there's our leakage resistance for the we'll say the stator. So X LS is equal to 12J, and then we have our rotor resistance, which is unknown, so R prime R, and then now we have another resistance here, so this resistance is going to be, or this impedance is going to be the rotor resistance, the rotor leakage resistance. So we'll do X prime LR is equal to 12J. And then this is going to be another resistance here. This is going to be R prime R over S times 1 over S. Okay. So this is our circuit with an ideal transformer model. Okay, we're going to want to use an ideal transformer model for this problem. Okay. So part A asks us to find our rotor resistance, R prime R, such that our slip at max torque is equal to 0.1. Okay, so luckily we have a slip at max torque equation. So SMT is equal to R prime over our two leakage resistances. Okay. So what we're going to do is we're going to plug in our knowns. So R prime is equal to, let's see, SMT is equal to 0.1 times 12 plus 12. That means that R prime is equal to 2.4. Right? Awesome. Okay, part A down. Now, for part B, let's see. So for part B, we are trying to find the torque from electric origin as a function of S. And then once we do that, then we can use this function to solve for the torque of electric origin at the starting point. Okay. So our torque of electric origin as a function of S, or in general, our torque of electric origin is equal to this equation. That's going to be poles over 2 times 3 times our voltage, our phase voltage squared, times our rotator resistance over S omega S, our slip times omega S over RA plus, excuse me, RS prime over S squared plus X LS plus XLR prime squared. Okay, so now that we have our equation for torque from electric origin, let's go ahead and plug in some values. So we know that P is 6, so 6 over 2. And then next we have our phase voltage, so 3 times 440 volts over the square root of 3 squared. And then now we have our rotator resistance, our rotor resistance, which we don't know. So we'll keep that. Or, I'm sorry, we do know. 2.4. So 2.4 ohms over S, which we don't know. And then next we're going to have omega S, and omega S is going to be 2 pi 60 hertz, right? Over RA. We assume RA to be 0. And next we'll have RS prime, or our rotator resistance. So we'll have 2.4 over S squared plus, it's freezing up on me, plus our reluctances. I'm sorry, not our reluctances, our leakage resistances. Okay, so we are going to have, let's see, 12 plus 12, right? Squared. So 12 plus 12 squared. Okay, so let's go ahead and let's plug some of these values into our calculator. For the numerator of our fraction, we're going to get 3,697.49 over S. Next, 2.4 squared is 5.76, so 5.76 over S squared plus 24 squared, which is going to be 576. Okay, let's go ahead and let's multiply our function by S squared over S squared, just to make sure we don't have any S's in the denominators. So we'll get TE is equal to 3697.49 S over 5.76 plus 576 S squared. Okay, so this is our function of torque from electric origin as a function of spin. Oh, sorry, of slip. Next, let's go ahead and let's find our torque from electric origin at the start, or at start. Okay, so torque from electric origin at start, excuse me, at start means that our S value is equal to 1. That's why we found our torque from electric origin as a function of slip, or S. So let's go ahead and let's plug in S equals 1 to our equation. So T of 1 is equal to 3697.49 times 1 over 5.76 plus 576.1 squared. And that's going to equal, let me put this in the calculator real quick, 3697.49 over 5.76 plus 576. That's going to give us 6.355 Newton meters. So that should be our final answer. If you have any questions on how we did this, please let me know. And with that, I think we're good to go. Thank you for watching.